In this question, number 31, we want to find the center of mass of capital letter F, which is cut from a uniform metal sheet. Your metal sheet is uniform, so mass per unit area will be constant. Let's say sigma is mass per unit area, so it will be constant. We have divided this whole letter in 4 segments. This is first, second, third and fourth. This point is taken as origin. Individually we'll find location of center of mass for each component, and then finally we'll find xcm and ycm for whole letter. First, taking the coordinates for first component. This length, this is along x-axis, it is 6 and this height is 2 meter. For uniform distribution of mass, we know that center of mass is located at geometric center. So for this, geometric center will be at this point, which is at 3 meter horizontal distance and 1 meter vertical distance from A. So center of mass of object 1 will have x coordinate as 3 and y coordinate as 1. Now for second component, its length is 2 meter and height is also 2 meter, so its center of mass will be again its geometric center. It is having distance 1 meter from A along x-axis, and it is having total 2 plus 1 3 meter distance along y-axis. So center of mass of 2 will have coordinates 1 and 3. Same way, writing for third component, this total length will be, this length is 2, this length is also 2, so total length is 4. So along x-axis, the center of mass coordinate will be 2 and this height will be 1, as this total height is 2. So this is 4 plus 1, so y component will be 5. For fourth component, the center of mass will be geometric center, so x component will be 1 and y component will be, this height is 2 plus 2 plus 6 plus 1, that will be 7. Now we want to find the mass of each component. m1 is equals to sigma into a1, m2 is equals to sigma into a2, m3 is equals to sigma into a3, and m4 is equals to sigma into a4. So m1 will be, area of this component will be 12, so mass will be 12 sigma. For m2, area will be 4, so mass will be 4 sigma. For this component, area will be 4 into 2, that will be 8 sigma. And again for this component, m4 will be 4 sigma. Now the xcm will be m1 x1 plus m2 x2 plus m3 x3 plus m4 x4 upon total mass m. m1 is 12 sigma, x1 is 3, so that will give us 36 sigma. m2 is 4 into 1, so 4 sigma, plus, from this equations we can find xcm and ycm. By solving this, we will get xcm as 15 by 7 and ycm as 23 by 7. So option 2 is correct option. In question number 32, two particles of equal mass are given. They are having initial velocities as 4 I cap and v2 as 4 j cap. The first particle has an acceleration of phi I cap plus phi j cap, and acceleration of second particle is 0. We want to find the path followed by center of mass. First we'll find the velocity and acceleration of center of mass. Initial velocity of center of mass is equals to m1 v1, that is 4 I cap, plus m2 v2, that is m4 j cap, upon total mass, that is 2m. This will be 2I plus 2j. As acceleration of second mass particle is 0, then acceleration of center of mass will be m phi I plus phi j plus 0 divided by total mass 2m. So acceleration of center of mass will be 2.5 I cap plus 2.5 g cap. Here from the equations of velocity of center of mass and acceleration of center of mass, we can say that velocity and acceleration are parallel to each other. ACM is parallel to VCM. That means force acting on the particle is in the direction of its velocity. So particle or center of mass will follow the straight line. So first option is correct. In question number 33, two identical circular plates, each of mass 0.1 kg and radius 10 centimeter, that is 0.1 meter, are joined as shown in figure. We want to find the moment of inertia about their common tangent, that is I. Now for a circular disc or circular plate, we know the moment of inertia about the point, about the axis passing through the center and perpendicular to the plane, that is ICM is mr square by 2. Now we want to find the moment of inertia about this tangent. First we will use the perpendicular axis theorem. According to perpendicular axis theorem, if any two-dimensional object is kept in xy plane, then moment of inertia about z-axis is equals to moment of inertia about x-axis plus moment of inertia about y-axis. Here we are assuming that these discs are kept in xy plane. We know the moment of inertia about z-axis, so Iz is mr square by 2. Now this is the x-axis and this is the y-axis. As x-axis and y-axis divide this plate equally, then moment of inertia about x-axis and moment of inertia about y-axis will be same. So we can write it as 2Iy. So Iy is equals to mr square by 4. So moment of inertia about this axis is Iy. For plate 1, moment of inertia about this axis. For that we have to shift Iy by distance r. So we will use parallel axis theorem. So moment of inertia of plate 1 about this axis will be I1 is equals to mr square by 4 plus mr square. This will give us 5 mr square by 4. For plate 2 also it will be same. So I2 will be 5 mr square by 4. So total moment of inertia of the system will be I1 plus I2, that will be 2.5 mr square. Put the value of mass and radius in the equation. So I will be 2.5 into 10 power minus 3 kg meter square. So option 2 is correct option. In question number 34, two spheres are given, nothing is said, so we will consider them as a solid sphere. They both are identical, they have mass m and radius r by 2. They are separated, their centers are separated by distance 2r. They are connected with the help of light rod. We want to find the moment of inertia of the system about this axis. Let's say total moment of inertia of the system is I. Moment of inertia of this sphere about this axis is I1, and moment of inertia of the sphere about this axis is I2. Here I1 will be simply 2 by 5 m r by 2 whole square. So it will be 2 by 5 mr square by 4. So this will give us mr square by 10. Now to find the moment of inertia of second sphere, we know the moment of inertia about this axis, then we have to shift it parallelly by distance 2r. So we will use parallel axis theorem for sphere 2. So I2 will be moment of inertia about this axis will be same mr square by 10 plus shifted by distance 2r, that will be m 2r whole square. So I2 will be mr square by 10 plus 4 mr square. Total moment of inertia of the system will be I1 plus I2. Put the values, mr square by 10 2 times plus 4 mr square. So answer will be 21 by 5 mr square. So option 1 is correct option. In question number 35, it is given that moment of inertia of a thin circular plate about its natural axis. Natural axis is the axis passing from the center and perpendicular to this plane is I. Let us assume that mass of this plate is capital M and radius is capital R. So I will be mr square by 2. We want to find the moment of inertia of a ring having mass small m, let's say, and radius small r, passing through any tangent of the ring. Let's say we want to find the moment of inertia about this tangent. This is I dash. First we have to find the moment of inertia of the ring about this axis, that means y axis, and then we will shift it parallelly by distance small r. The moment of inertia of ring about its natural axis is mr square, and moment of inertia of this ring about y-axis is mr square by 2. We can find this by using perpendicular axis theorem. Now I dash will be mr square by 2, and shift this moment of inertia axis of rotation by distance r plus mr square. So I dash will be 3 by 2 mr square. Here the relation between mass and radius of ring and circular plate are given. The mass of ring is half of mass of circular plate, and radius of the ring is 2 times the radius of circular plate. Put these values in this equation. I dash is equals to 3 by 2, m is equals to capital M by 2 into r is 2r whole square. So I dash is equals to 3 by 2 into 4 mr square by 2, but mr square by 2 can be written as I. So I dash is equals to 6i. So option 3 is correct option. In question number 36, a uniform circular disc of radius r is given. Let us assume its mass is capital M. It is located such that its center lies at the origin. Now it is said in the question that moment of inertia of this disc about the point which is located at x is equals to 2r and perpendicular to this point is equal to the moment of inertia about this axis, which is parallel to x-axis, and distance between x-axis and this axis of rotation is d. If this both moment of inertia are same, we want to find this distance d. First we will write moment of inertia about this point. For given disk, we know the moment of inertia of the axis passing from point O and perpendicular to the plane, that is m r square by 2. We want to find moment of inertia passing from this point and perpendicular to this plane, so simply we have to shift it parallelly by distance 2r. Now to find moment of inertia about this point, first we have to find the moment of inertia about x-axis. We know that moment of inertia of the disk about x-axis will be mr square by 4. So moment of inertia about this axis will be I is equals to mr square by 4 plus shifted parallelly by distance d, so m d square. It is given that this both values are same, so we can compare 9 by 2 mr square is equals to mr square by 4 plus m d square. Simplified, we want to find the value of d. By simplifying, we'll get d is equals to under root 17 by 2 r. So option 2 is correct option. In question number 37, it is given that a ceiling fan is rotating initially with speed omega. When current is switched off due to constant opposing torque, its angular velocity is reduced to 2 omega by 3 after completing 30 revolutions or 30 rotations. We want to find the number of rotations further it makes before coming to rest. We'll use this equation that omega square is equals to omega naught square plus 2 alpha theta. Here we'll take theta as directly number of rotation. In this case, the final velocity is 2 omega by 3 whole square is equals to initial is omega square plus 2 alpha, number of rotations made is 30. Simplify this, 4 omega square by 9 minus omega square is equals to 60 alpha. So minus 5 omega square by 9 is equals to 2 alpha into 30. Now let us find the number of rotations made by fan from omega to 0 velocity. So 0 is equals to omega square plus 2 alpha theta dash. So omega square is equals to 2 alpha theta dash. Value of 2 alpha will be minus 5 omega square divided by 9 into 1 by 30. This omega square will get cancelled out. So theta dash will be 54. So total number of revolutions or rotations it made before coming to rest is 54. You have been asked how many further revolutions. That means 54 minus 30 is equals to total 24 revolutions it will make. So option 4 is correct option. In question number 38, it is given that moment of inertia of a ballet dancer decreases by 20%. So I2 is equals to 0.8 of I1. I2 is final moment of inertia, I1 is initial moment of inertia. We want to find the percentage change in its rotational kinetic energy. Here, due to change in moment of inertia, angular velocity will also change. So first we'll use conservation of angular momentum L. That means I1 omega 1 is equals to I2 omega 2. So omega 2 by omega 1 is equals to I1 by I2. So I1 by I2, from this equation we can write 10 by 8, that is 5 by 4. Now let's say E2 is the final rotational kinetic energy and E1 is the initial rotational kinetic energy. E2 will be half I2 omega 2 square divided by E1 half I1 omega 1 square. From this I2 by I1 we can write 0.8, that is 8 by 10, into omega 2 by omega 1 is 25 divided by 16. Simplify this, we'll get 5 by 4. So E2 by E1 is equals to 5 by 4. For percentage change, we'll use this formula, E2 minus E1 upon E1 into 100. By solving this, we'll get 25%. As I is decreasing, omega will increase, so kinetic energy will increase. So kinetic energy will increase by 25%. So option 3 is correct option. In question number 39, a barrel answer is decreasing its radius of gyration by 20%. That means R2 is equals to 0.8 R1. Now we know that I is directly proportional to R square. So I2 by I1 is equals to R2 by R1 whole square. From this we can write 0.8 square. So I2 by I1 will be 16 by 25. Now as there is no external torque is acting, we can use conservation of angular momentum. So I1 omega 1 is equals to I2 omega 2. We want to find omega 2. So omega 2 will be I1 by I2 into omega 1. I1 by I2 is 25 by 16 into omega 1 is 1.6. By solving this, we'll get omega 2 as 2.5 rotation per second. So option 2 is correct option. In question number 40, a circular disk with time period 0.2 is rotating about a fixed vertical axis. Another identical disk is placed on it. We want to find the new time period of the combined system. Here no external torque is acting on the system, so we can use conservation of angular momentum. So I omega is equals to I dash omega dash. Initially there was only one disk. Let's say its moment of inertia is I, and omega we can write as 2 pi by t, and time period is 0.2. Now there are two identical disks, so combined moment of inertia will be 2I and omega dash will be 2 pi by t dash. Simplify this, we will get t dash is equals to 0.4 second. So option 4 is correct option. In question number 41, it is given that a sphere is rolling on a rough horizontal surface with a linear speed v. It collides elastically with a fixed smooth vertical wall. What is the speed of the sphere after it has started pure rolling in backward direction? It was rolling initially in this direction, and now after collision it will start rolling in opposite direction. Here the collision is elastic, so linear momentum and angular momentum are conserved. So angular momentum of the system is conserved. The angular momentum just after collision can be written as mvr minus mi omega. And angular momentum sometimes after collision can be written as m v dash r plus I omega dash. This both angular momentums are same, so we will compare it. mvr minus I omega can be written as v by r is equals to m v dash r plus I omega dash can be written as v dash by r. I for solid sphere is 2 by 5 mr square, so mvr minus 2 by 5 mr square into v by r is equals to mv dash r plus 2 by 5 m r square into v dash by r. Solve this equation for v dash. We will get v dash is equals to 3v by 7. So option 3 is correct option. Question number 42. Moment of inertia of disk is given as 1 kg meter square and it is rotating with angular velocity 100 radian per second. Now another identical disk is gently placed on this. We want to find the loss in kinetic energy. The loss in kinetic energy will be I2 omega 2 square minus original kinetic energy half I1 omega 1 square. For that we have to know the final angular velocity of the system. We will use conservation of angular momentum. So I1 omega 1 is equals to I2 omega 2. Initially there was only one disk, so moment of inertia will be 1 into its angular velocity 100 is equals to. Now two identical disks are rotating, so total moment of inertia will be 2 into omega 2. So omega 2 will be 50 radian per second. Now loss in kinetic energy is equals to final kinetic energy minus initial kinetic energy. For final kinetic energy, we'll use 2 times kinetic energy of each disk minus initial kinetic energy. Only one disk was rotating, so I omega 1 square. 2 into 1 by 2, I is 1, omega 2 is 50, so 50 square minus 1 by 2, I is 1, omega 1 was 100, so 100 square. Simplify this, we'll get answer 2.5 kilojoule. So option 1 is correct option. In question number 43, a circular ring starts rolling down an inclined plane. When it reaches the bottom, its velocity is v. From the same plane, a block starts sliding and its velocity is v dash. We want to find v dash. We know for this case v is equals to under root 2gh upon 1 plus I upon mr square. Here I is the moment of inertia of ring, that is mr square. Put this value, we'll get v is equals to root gh. And for block, v dash will be root 2gh. So we can write v dash is equals to root 2v. So option 4 is correct option. In question number 44, a thin uniform rod of length L is bent from its midpoint. So this length will be L by 2 and this length will also be L by 2. Mass of this portion will be m by 2 and mass of this portion will also be m by 2. The angle between them is theta. We want to find the new position of center of mass of the system from this point. Let's say this is x-axis. So x coordinate of center of mass is equals to, for this point it will be L by 4 from origin as it will be the geometric center of the rod. So m1 x1 plus m2 x2 upon m1 plus m2 using this formula. m1 is m by 2, x1 is l by 2 plus m2 is m by 2 and x2 is l by 2 l by 4 cos theta divided by total mass of the system, that is m. For YCM we will write, for this y coordinate is 0, so only this rod is considered. Mass is m by 2 and y coordinate will be l by 4 sin theta divided by total mass of the system. So XCM will be L by 8 plus L by 8 cos theta and YCM will be L by 8 sin theta. Now we have taken this point as origin. We want to find the position of center of mass. The position vector's magnitude will be under root XCM square plus YCM square. Put this value in this equation, we'll get R magnitude is equals to L by 4 cos theta by 2. So option 4 is correct option. In question number 45, translatory kinetic energy of a rolling solid sphere is given. Translatory kinetic energy is half mv square, that is given as 35 joule. We want to find its total kinetic energy. Total kinetic energy is half I omega square plus half m v square. Half moment of inertia of solid sphere is 2 by 5 mr square. Omega square we can write as v square upon r square plus half m v square. So this can be written as 2 by 5. This r square will get cancelled out into half m v square plus half m v square. But we know that half m v square is 35. So 2 by 5 into 35 plus 35. Simplify this, we'll get answer 49 joule. So option 2 is correct.